So in this video of the lesson, we are going to begin to show how we use matrices, specifically the augmented matrix of a system of equations, to solve the system. In order to do this, we need to define our end goal, what it means to actually fully reduce the matrix so that we obtain the solution. We call this matrix reduced row echelon form. For those of you who are bilingual or multilingual, the word echelon means or shares a common root with, let me pick, let's do this, a color that hasn't already been used. How about this orange one? So it sounds familiar to Echelon, which, if I'm not mistaken, is the Spanish word for stairs. And so we can see this same root, and having a staircase pattern in mind is going to help us visually remember this definition. Reduced row echelon form is a mouthful. And so most mathematicians, once they have memorized what it stands for, just say RREF, or REF if you want to roll your arms. I like linguistic puns. In any case, there are 4 criteria that tell us a matrix is in reduced row echelon form. Every column has exactly one 1 in it. So it has one copy of the number 1, and that's in each column. The second thing, every other number in the matrix is 0. So our matrix is full of 0s and 1s. Any row with only 0s is moved to the bottom. And lastly, the 1s in each column form a descending staircase pattern. So if we come back to this idea of a staircase, we want that staircase pattern to be clear. Sometimes the steps will differ in height or width, but as long as we have that staircase shape, it's in reduced row echelon form. So one last note is that these criteria do not apply to the rightmost column, so the constants of an augmented matrix. We're only interested in the square portion. So we have a couple examples. So notice that in this first example, we can draw that staircase shape descending along this main diagonal. Every column has 1, 0. Every other number in the matrix is 0. The second one, we still have this staircase pattern. And notice that because there's this dividing line, we don't really care what the numbers in the augmented portion of the matrix are. As long as the square is in reduced row echelon form, the entire matrix is considered RREF. So counterexamples, we have this staircase pattern. However, this is not a 1, and these numbers are not 0. So we could eventually make this reduced row echelon form, but it would require some additional work. In the second example, we have the 1s and we have the 0s. However, in this case, our stairs go upwards, and we specifically want a descending staircase. We want to go down the stairs, not up the stairs. So you can think of it as going down the stairs is less work, going up the stairs is more work, and we want to minimize the amount of work. So making sure that these stairs are in the right direction is important. Notice, as an extra fact, that if we take row 1 and row 2 and switch them with each other, our two bottom matrices would be the same. So we can flip the order of the rows to change the direction of the staircase. In addition to reduced row echelon form, we need to discuss the tools that allow us to get there. And so what that means is actually switching two rows is the first rule. And I know I have this a little bit further down as well, but we use a double pointed arrow to represent the two rows that we're switching. We can also multiply a row by a non-zero constant. For example, if A is any number, you can multiply A or R1 by A. By extension, this means we can also divide, but by dividing, we really think we're multiplying by the reciprocal. So if I divide the entire row by A, it's like multiplying by 1 over A. Lastly, we can also add a multiple of one row to another. So we might say R1 plus 2 times R3. Notice that these are the same tools that we used when solving a system of equations using elimination. Now we're just formalizing these and giving them some special notation. The reason we call them elementary row operations is because if you take enough classes in linear algebra, you'll find more things that you can do with the rows, more operations that are not elementary. We are not going to ever get to those in this course. You might even need to go as far as a graduate level math class to see those other operations. So for the sake of our purposes, these are the three things we can do to a matrix to solve an equation. So here in slightly more clarified terms are the notation examples, that double-faced arrow for switching, just writing a number before the row number for multiplying, and adding just as we did before. A point of vocabulary worth mentioning is that when using elementary row operations, one row, which technically we call the pivot for reasons I'm not entirely sure, must be fixed in place and not changed between that step and the next step. So if we have 3 rows in our matrix, we can change 2 of them using the third, but that third one must remain unchanged. We usually label our pivot with a star or an asterisk or a similar symbol so that we are aware what row is changing and how, and what row isn't changing and why not. So I think for timing on this video, we'll do an example. So we'll do one example in this video and then a couple more examples on their own. So we want to solve this system of equations using a matrix. So we need to remember to first write the augmented matrix and then use our row operations to rewrite the matrix in RREF, so reduced row echelon form. Before I get started, I encourage you to pause and practice writing that augmented matrix. In fact, it might be a good practice to pause before most steps or between steps of a question, so that you can, write your work, press play, and see if your work matches. And if not, figure out why not. So I will assume as we go through that if you want to pause, you will be pausing. I will try to be conscious of creating a space between words to pause rather than just saying it repeatedly. So again, pause the video, attempt this question, writing the augmented matrix, hit play, and continue. So our augmented matrix is always the coefficients of our variables, a vertical line to represent the equal sign, and then the constant terms. So reading across, we have 3, 1, 5, and 5, -4, -3. And our goal is to get a matrix where you have 1, 0, 0, 1. This is that reduced row echelon form that we want. And on the right side, we'll have some number that represents our x value and some number that represents our y value. We don't know what those numbers are yet, but we will. So to begin, we want to think about those 3 options that we have. And so looking at this, I see there is a 1 here. Whenever there's a 1, it's really straightforward to, it's really straightforward to eliminate a number and make that entry 0. I'm copying this only because I didn't want to erase the goal part. So what we're going to do is, because I'm going to use this 1 to get rid of the -4 beneath it, this first row is our pivot. So I'm going to mark it with a star. And then the second row, I'm going to replace with row 2 plus 4 times row 1, because -4 plus 4 times 1 is 0. One thing that I like to do, and this is where it's really helpful to use multiple colors or to give yourself a lot of space, is to write underneath the entry in the matrix what I'm adding to it. So this is row 2, and I'm adding 4 times row 1. So 4 times 3 is 12. 4 times 1 is +4. And then 5 times 4 is 20. And so now, when I rewrite my matrix on the next line, the first row doesn't change because we said that's our pivot. The second row, 5 plus 12, is 17. -4 plus 4 is 0. And -3 plus 20 is 17. Now, I ultimately want to get to 1s and 0s. And so I can see that I have a 17 in both parts of row 2. So I'm going to replace row 2 with 1/17 times row 2, because 1/17 times 17 is just 1. In this case, row 1 is still technically a pivot because it's not changing, but we wouldn't label it the pivot because we're not doing anything with the row. It's just staying the same. So we have 3, 1, 5, And if we wanted to continue this over here, we could just divide all of our numbers. Of course, when you're writing 17, you should be careful not to write 12 instead. So we're dividing each number by 17. So when we get to our next matrix, we'll have 1. 0 divided by anything is still 0, and then 1. We can now use the 1 that we've obtained in our second row to cancel out the 3 in the first row. Since I'm using row 2 to modify row 1, I'm going to put a star beside it because it's our pivot. And then we're going to do row 1. In order to cancel out the 3, I need to subtract -3 times row 2. And once more, I'm going to write next to the numbers what I need to change. So I'm subtracting 3 times 1, which would be -3. Then I'm subtracting 0 times 3, which is 0. And over here, it's going to be -3 again because we have another 1. Three minus 3 is 0. 1 minus 1 is 0. 5 minus 3 is 2. And then our second row didn't change. Now we are very close to being finished because we have all the right numbers, but they're in the wrong places. So I'm going to note over here that we are switching rows 1 and 2. So our final matrix is going to be 1, 0, 1. Notice that that was what used to be row 2. And then our first row comes down to the second spot. So we have 0, 1, 2. Now, this is reduced row echelon form. And we can give our solution. So the solution, again, we can give it as a point or a list of variables. So the point would be 1, 2, remembering it represents our x and then our y. Or we could have x equals 1 and y equals 2. If you're typing this, you might write x equals 1, y equals 2. In either case, this is our solution, and we got here using our row operations. And because we have this more concise method of noting what we're doing, it actually appears to be less work than it would have taken if we had solved it just using elimination in a more traditional sense. So this is where I'm going to end this video, but I will follow it up with a couple more examples to continue illustrating how we use these row operations to solve a system of equations using a matrix.